In this video we will take a look at the individual components that have been used to make up a wireless controlled LED lights and sound circuit. The operation of the circuit was shown in some detail in my earlier video, but as a refresher let's take a quick look at the functions again. The first stage is to switch the main power on, in this case a constant 5-volt supply, to put the circuit in standby mode. We use the breadboard power module on switch for this purpose. Here. Now let's look at the 4-channel transmitter, which will be used from now on to access the light and sound functions. This is a simple unit with 4 switches and a neat extending aerial. By pressing switch A of the wireless transmitter, the system boots up into full power mode in 3 stages. First, the red bar will come on. The second stage, the green bars will come on. Also the flashing LEDs, lower flashing LEDs, and some stationary LEDs in this area. For the third stage, the top orange lights will come on and they will flash in a rotating pattern. So here we go. 1, 2, 3. Those are the 3 stages which occur automatically after switching on. Switch B of the wireless transmitter causes a sound clip to be played accompanied by synchronized flashing lights. Switch B.
Watch it, Will Robinson.
If we hit switch B again, the same sound clip is repeated.
Watch it, Will Robinson.
Whilst hitting switch C causes a new sound clip to play.
I compute it to be an ionic directional probe, searching for receiving outlets.
If we hit switch C again, we will again get a new sound clip.
That does not compute.
Switch D, the last on our 4-channel wireless remote, causes the lights to shut down and put the system back into standby mode. So now we have seen the system operating again, let's go to full power mode and look at the design in more detail. Switch A, full power mode. 3 stages are now completed. Perhaps a good place to start is the wireless transmitter and receiver. We have already seen the transmitter, which is a 4-channel unit and has a range of about 5 to 10 meters. This is perfectly adequate for this design and benefits from being a highly compact unit. The signal from the transmitter is detected by the wireless receiver. I'll zoom in on that component now. This unit has 7 connections. 1, 2, 3, 4, 5, 6, 7. 2 of these are to power the receiver board, 4 of the connections are for the channel outputs, and 1 is an indicator output which goes on whenever a channel is activated. The receiver output gives a high signal, and ideally this should go straight to the switching relays, which we can see to the right. But in this case we have active low relays, so we need to invert the receiver output signal to a low signal to trigger the relays. This is done by simply connecting the receiver output via a ULN 2003A inverter chip. We have one here, so let's zoom in on that. It's up the top to the right. This is a 16-pin chip. 2 pins supply power to the chip, and the other 14 pins consist of inputs/outputs for 7 independent inverters, of which we're only using 4 for this project. If we look at this chip in more detail, These are the input pins, and these are the wires coming from the wireless receiver. Those signals are inverted and go out via the output pins of the inverter. So let's follow the wires of the output pins and see where they go. So we're going down here, continuing. We hit some connections here and around, some more connections. This will all be tidied up in the final version, of course, and go into the inputs of the relays. So the inverted signal goes to the input pin of a corresponding relay to energize it. Looking at these relays, there is a bank of 2x2. I've numbered them 1, 2, 3, 4 from left to right. These have a power supply to them, which is indicated by the green LEDs, but the relays are not actually energized until they receive an input signal. When this happens, a red LED lights up to show the relay has been activated. For this circuit, relay 1 switches on and stays on. This is known as a self-lock relay, and this is why we can already see a red light on here. This relay was energized earlier to power up all the lighting functions. Relay 2 is a momentary relay, and all it does is short 2 pins on the sound card, much as pressing a switch would do, which is how the card was originally supplied. So let's operate relay 2 and we will see a response from the sound card.
That does not compute.
This is the original switch that we got with the sound card. So we press the switch there and that makes contact with those 2 pins there. We are replacing that with the relay so that action occurs via the wireless transmitter. It's all electronic rather than manual. Relay 3 is similar to relay 2, but it shorts 2 different pins on the sound card. Hence this is how we get a different sound clip to play. So if I press switch C of our remote, we will see relay 3 will operate.
I am sorry, Will Robinson. I am afraid I goofed.
We only need to make contact for the sound card to respond, so once the relay has made contact, it can be released. Relay 4 cuts the power to relay 1, as this is the only way we can get a self-lock relay to switch off. Switching relay 1 off is equivalent to cutting the power to lighting circuits. So at the moment we still have our lighting circuits operating as the power is going through relay 1. Operating relay 4 now, we will see not only does relay 1 switch off, but all power to the board is actually cut. There we go. Relay 4 went on, all power to the board was cut. As soon as relay 4 goes off, power to the board is restored, but relay 1 will not energize until it receives a signal from the transmitter. So now we can see all the lights are switched off except the standby lights. And if we press switch A of our transmitter, we will operate relay 1, which will switch on and lock on. So that locks on and our lights return and stay on due to the locking motion. As the lighting circuits switch on in stages, which we saw, one was immediate and there were 2 delays. These delays are built into the design. The first delay consists of an LM358 dual op amp chip. Let's zoom in on that. So it's to the top left. this is our op amp chip here, hidden in that tangle of wires. This is an 8-pin chip which has 2 sets of inputs and 2 outputs. I've used it to compare a reference voltage going into the inverter pin. So the reference voltage is split using 2 resistors as a voltage divider. So our 2 voltage divider resistors are here and here. This is compared against an increasing voltage going into the non-inverting pin using an RC resistor capacitor circuit. So that here is the capacitor and here is the resistor of the RC circuit which goes into the non-inverted pin of the op amp. When the non-inverting voltage increases above the reference voltage, the chip provides a source current on the output pins. I'm feeding this current directly to the white LEDs, so the output from the op amp goes directly to the white LEDs and also to the green bar LEDs, to the 2 sets of green bar LEDs. The second output from the LM358 op amp chip goes to a pulse generator module, which we can see here. So that output is powering the pulse generator module. The pulse generator module produces a square wave pulse that can be adjusted for both frequency and duty cycle using the onboard potentiometer adjusters. I'll show that in operation now. If we make an adjustment to the potentiometer here, if we go anti-clockwise to the left, the output signal decreases in frequency, and if we turn to the right, the output signal increases in frequency. This will have a direct effect on our lower flashing LEDs, as I will show in more detail later. At the moment we put it back to what is quite a nice rate for this circuit. Perhaps a little bit faster than that. There we go. That's a reasonable rate. This square wave pulse is fed into a 4017 decade counter chip, which is a 16-pin chip, and we can zoom in on that. So that pulse comes through, goes into our pulse generator chip here. The chip is there, again hidden in a tangle of wires, because there are 16 connections to be made. This directs the input pulse to one of 10 outputs in a repeating sequence, and this is where I have connected my flashing LEDs and also the wigwags. So the output from the decade counter goes to the wigwags, which are the red and green alternate flashing at the top, and also to my lower flashing LEDs. Regarding the wigwags, these are reverse biased to each other and connected to pin 12 of the decade counter, which outputs low on counts 0 to 4, putting the red LED on, and output's high on counts 5 to 9, putting the green LED on. Let's go back to the flashing LEDs and I'll show you the effect of changing the frequency on the pulse generator. So bear with me. Decreasing the frequency now, we can see that the LEDs flash at a slower rate, and we can increase that frequency and they flash at a faster rate. We can have any flashing rate we like, as you can see. There is also a switch on the board which connects directly to the decade counter. It connects the output count 5 of the decade counter to the decade counter reset pin, so the chip only counts from 0 to 4 before repeating the count if we change the switch position. So let's do that now. We change the switch position and you will see the effect that will have on our flashing LEDs. So now, previously they were flashing with a delay because counts 0 to 4 were going straight to the LEDs and counts 5 to 9 were not connected to the LEDs. So whilst counts 5 to 9 were occurring, there was a delay in the flashing sequence. But now we only have counts 0 to 4, and that repeats, and so the flashing LEDs repeat continuously. Another effect of that is that it's had an effect on our wigwags. As we mentioned before, the red LED will be on for counts 0 to 4, and it remains on in this case, and the green LED goes on from counts 5 to 9, and that will not occur as we are no longer counting from 5 to 9. Right, let's reset our unit at this stage. Again, if we look at our flashing LEDs, which are now continuous, and we adjust the pulse generator, we will see the effect we get now with continuous flashing. That's faster, very fast, and we can slow right down. And back to a rate which is quite nice, something like that. A second delay circuit consists solely of an RC resistor capacitor timing circuit, and this gives us stage 3 of the boot up process. So that's on the top left hand, close to the first delay circuit, but this time there's no chip involved, it's just a capacitor and the corresponding resistor, which is here hidden behind that red wire. The red wire is the output from the RC circuit, and that goes to our flashing orange LED board here. All that happens there is, as the signal increases, it reaches a critical level, which then tells the board to switch on. This is only a low current signal, as the circuit board has a separate power supply to it, and therefore it's not required to actually power the board. The last part of this project is the voice synchronized flashing lights, and this is simply a plug-in module that reacts directly to the sound coming from the sound card. Let's go to that module. That's the flashing lights module there. If I take the module out from the board, we can see it in more detail and how it works. This is the flashing module. As you can see, there are only two inputs, which are the plus and the minus power inputs. There's no other input to this, so there's no other electrical connection between this and the sound card. The way it works is that the microphone here detects sound from the sound card and converts that into a weak electronic signal, which is then amplified by the transistors and some other circuits on the board to make the signal strong enough to power the LEDs. So that's quite straightforward. All we need to do is supply the power to this unit, and everything else will occur as the sound card works. So I'll try and plug that straight back in to where it should be on the board. If I find the right pins, and I did, we should find that this unit will operate immediately as soon as we get a sound clip.
You might be placing us all in deadly danger.
And it does, just as we would expect. Let's get nice and close, see that in operation.
That is not necessarily a true statement.
And while we are here, let's have a quick look at the sound card itself with the pin connections. This is the sound card. The sound card still has the original batteries attached to it, and it's still operating using those batteries, but I will remove those and I will power the sound card from my main board. We can see there are some connectors here, and this is where the original switch supplied with the card was connected. So that just plugged in straight there, and the card is operated manually by pressing this switch. So if we do that, we will get a sound.
That is not necessarily a true statement.
I've replaced that situation with the outputs from the relays, which are making contact directly using this plug unit. So that plugs in there. There are 4 cables here, but we're only actually using 2 of them. So they plug into the connectors there, and we put the sound card back in place. And if we operate the signal,
that is not necessarily a true statement.
we see the relays operating the sound card. I'm using this Light and Sounds project for a specific purpose, i.e. my Lost in Space TV robot project. Scale model, but I'm sure there are many more applications where similar arrangements can be used in different situations. So if you're inspired to do something similar using flashing lights and sound, I say to you, good luck with your project, and I wish you happy model making. For me, half the fun is figuring out what exactly I want to do, and the other half of the fun is actually getting it to work.